No, I'm having a lot of fun. This just hurts.
It does. It's hard, but it's good for you. Okay, so let's take a look. Check your table, see if that's what you got.
Whoa.
That's what I got.
Okay, so you have to take, you put 2 in there for the volume, and then you multiply by 3 divided by 4 pi. So you have to put that 4 pi is in the denominator. Okay, and then take a cube root. So if our volume formula is volume equals 4/3 pi r cubed, to get r, so r cubed would equal 3 over 4 pi times v, and then r would be the square root, the cube root of that. Okay, it'll be the cube root of it. Okay, because that pi is up top. When we divide over to the other side, it takes it to the bottom. That's the most common mistake right there. Okay, all right, but we can still move forward. Okay, we can still move forward if you need to get those. So correct those values if you need to. Okay, now how are we going to find the rate of change of the volume? Yeah, we can just look. All right, for every 1 second, how much is it changing? 2, okay? It works again the next time. For every 1 second, it's changing 2. So 2 volume cubic feet per second, all right? That is your rate of change. That is your dV/dt, okay, in the volume over time. Okay, so 2 cubic feet per second. And we can do that just by looking at the table. Lucky for us, they gave us that nice equal intervals there for time and for volume. Now, what about the radius? Is it, yes, sir? Huh? It is a huge balloon. All right, is the radius changing at a constant rate? Think about that. If you blow air into a balloon, what's going to happen over time? It's going to pop eventually, right? So when you first take the balloon, what's going to happen with the radius? Yes. But then as we put more and more air into it, what happens to the radius? It slows down. It doesn't expand as quickly, okay? Because that balloon doesn't have space for me to put, and it's a huge balloon, right? He's out here, okay? So he's changing a lot. And we got some kind of pump if I'm putting 2 cubic feet of air in there every second, okay? Like that's a lot of air. So is it changing at a constant rate? We would say no, okay? As the balloon expands, there's less space for the radius to change. So this was more common sense to me than mathematics, okay? All right, so not to overcomplicate it, all right? But we could actually look at the difference in the radii and notice it gets it gets smaller and smaller each time in terms of how it's changing. All right. So now let's get mathematical. All right. So the volume of the balloon depends on how much time has passed. We can rewrite our volume function as a function of time. So notice they did that. V of t equals 4/3 pi r of t cubed. So they rewrote it as a composition. Okay. What's the independent variable? Time. Okay. And so now we want to write an equation for dV/dt, all right, which means we're just going to take the derivative of both sides of this equation. So if I start with V of t, its derivative would be dV/dt equals, okay, r of t is my function, 4/3 pi is my coefficient. So if I take 3 times 4/3, what am I going to get? 4 pi. R of t is going to go to what power? The second. And I have to take the derivative of the inside stuff, which would be my dr dt, the derivative of that function. Okay? So it's just a chain rule. Yes.
May I use the restroom?
Yes. Okay. Gosh, I thought that was going to be a great insight into this rate of change problem. Samuel is a man of few words. All right, so then it says, at the instance when the radius is 1.5 feet, how fast is the radius changing? It's telling me I'm going to need my answer from question 3, okay? Well, let's go in and let's substitute, all right? If the radius is 1.5, so I have 4 pi times 1.5 squared dr dt equals, and then dv dt. What was that up in question 3? How was my volume changing? 2. So that's what I'm going to put on that side. All right? And then I'm going to solve that equation for dr dt. Okay. So if we solve, we'd get 2 equals 4 pi times 2.25. Okay, dr dt. And then to get dr dt, it's going to equal 2 divided by all of this, 4 pi times 2.25. All right, we're definitely going to get a decimal. It's definitely going to be a calculator question. All right. Okay, now let's think about our units. We're talking about the radius, okay, and how it's changing. How's the radius measured? Feet, and how's time measured? Seconds. Okay, so I get 0.071 feet per second. Okay.
So that is the rate at which the radius changes when the radius is 1.5 feet.
Yes.
Okay.
Yep.
Cool.
Because that rate of change is going to differ based on what instant I'm talking about for my radius. Okay. So now the last question, is the radius growing faster when the radius is small or when the radius is large? Think about that. Just think about the balloon itself. It'd have to grow faster when? When it's small, in the beginning. Because as my radius of my balloon gets larger, I have less and less room for it to change. Okay? So we would say that it grows faster when the radius is small. Okay? So since the volume, the rate of change of the volume is constant, a small radius means a large rate of change. Okay. Yes.
Random question. As the radius approaches 0, would the rate at which it changes approach infinity?
No,
No.
because
Okay.
it's got a specified space.
Okay.
Okay.
So it doesn't start out just
No.
incredibly fast.
No.
Okay.
What does that say? It means a what?
Large DRDT value, rate of change for the radius. Okay, congratulations, you just did your first related rate problem. Okay, we're going to spend all day tomorrow looking at a plethora of related rate problems and all the different mathematics and geometry, that can be used to solve those. Okay, these are primarily geometric based problems. Okay, just as a heads up. All right, today we're just going to start the process of learning how to differentiate with respect to time because it's kind of an abstract concept. All right, so derivatives with respect to time. Okay, derivatives with respect to time. We take a known formula and make time the independent variable. Thank you. Okay, so we take a known formula and we make time the independent variable. When we take our derivative, every variable gets a rate of change. with respect to time. Okay, so if there's an x, we get a dx dt. If there's a y, we get a dy dt. If there's a p, we get a dp dt. Okay, every variable gets a rate of change with respect to time. All right, so I just want to show you some basic examples today just to get you used to kind of this process. And then tomorrow we'll get into the gnarly problems. Okay, and hopefully our balloons won't be 2 feet volumes changing like that, right? That they'll make a little more sense. Okay. Okay, so let's look at a couple of these. There's no need for us to do them all, but we're just going to look at a few of them. Okay, like I said, we're going to keep it simple today. Okay, so look at this one. It says, given x and y are differentiable functions of time and are related by the equation y equals x squared plus 3. We want to find dy dt when x is 1 and dx dt is 3. Here's the thing. Do not substitute until after you take a derivative. Okay, so you have to differentiate first. So let's take that equation and let's differentiate with respect to time. What would be the derivative of just a plain y? Y prime. So dy dt is going to equal, what would be the derivative of x squared? 2x dx, everybody gets a d something dt. Okay, what would be the derivative of 3? 0. And now we just want to plug in what they gave me. They gave me that x was 1 and dx dt was 3. So dy dt is going to equal 2 times 1 times 3, which is just what? 6. Okay, so that's the most basic. All right, and they give you an equation, you differentiate with respect to time, and then you substitute. Okay. All right, let's do one where we need a geometric formula. Let's keep it 2D. All right, and let's talk about a rectangle. A rectangle is undergoing changes to its length and width over time. What is the rate of change of its perimeter over time? Okay, so I got a length and I got a width. How do I find perimeter of a rectangle? Okay, 2L plus 2W. And we're going to take a rate of change with respect to time for every variable. So what would be the derivative of P? dt. Every dp dt. Okay. What would be the derivative of a 2L? You got it. I don't even know what I just wrote right there. dl dt. And then the derivative of 2W. And that's it. Okay, so just getting in that habit of when it's with respect to time, it's a chain rule for everybody. Everybody is a function of time. Y'all try the next one. Say it. It's a product rule. Good job. Because you're multiplying two variables.
Everyone went, oh, it's gonna be like horrible.
No, it's not bad. Okay, so derivative of A, dA dt. We need product rule for the next one. So first, derivative of W, dW dt, plus second, which is W, derivative of the first, dL dt. Okay, yep, really missing the numbers right about now. Okay, lots of letters. All right, it would work the same way for a circle. All right, how do you find the area of a circle? Pi r squared. Okay, I want you to notice what happens right here. Okay? You get dAdt would equal, pi is a constant, all right? So 2 pi r dr dt. What's 2 pi r? It's the circumference, not a coinky dink. Okay? There you go. All right. So lots of cool things are about to come together. All right. So let me give you your assignment. Okay? Just 5 questions for you just to play with taking that derivative with respect to time. Okay? On page 264, 2, 3, 4, 5, and 6. Okay? And you do have a wrap up today. All right. I won't look at it till tomorrow, but make yourself a note so you don't forget to do it.
4-4.
It is 4-4.
Okay, so basically.
Length of the size of the cube changes over time. What the freak?
Like, oh, the size of it.